A molecule polluting water could become the molecule that feeds half the world. This is HQRS. Nitrate flows from fertilizer runoff and industrial waste into water. Inside an electrochemical reactor, that same nitrate meets a metal surface, receives electrons, loses oxygen, and leaves as ammonia. The central question is simple: can electricity turn a pollutant into useful fertilizer feedstock without the heat and pressure of conventional ammonia production? A nitrate ion contains one nitrogen atom surrounded by three oxygens. Ammonia keeps the nitrogen but replaces those oxygens with three hydrogens. Making that transformation is not one clean jump. It is a relay of reactions, and every intermediate can escape down the wrong pathway. Send too much reactive hydrogen to the surface, and it pairs with itself to form hydrogen gas. Hold nitrate too weakly, and it passes through. Hold intermediates too strongly, and the catalyst becomes clogged. In a 2026 peer-reviewed study, researchers built a nanoscale relay from silver and ruthenium. Silver begins the job, helping nitrate shed oxygen and become nitrite. Nearby ruthenium sites split water and manage adsorbed hydrogen, hydrogen temporarily held on the catalyst surface. Now watch the handoff. Nitrate reaches a silver-rich region. Electrons weaken its oxygen bonds. Nitrite moves through the catalyst's internal channels toward ruthenium. There, surface hydrogen attacks the remaining oxygen-containing intermediate step by step until ammonia detaches into the water. The researchers describe this as enzyme-like transport. Different regions specialize in different steps, while the structure keeps the reaction moving forward. Operando measurements, observations taken while the catalyst was actually working, plus theoretical calculations supported this mechanism. In the tested half-cell, 53.7% of the supplied electrical energy was stored in the ammonia product under one reported operating condition. The catalyst also reached nearly 100% Faradaic efficiency across a range of nitrate concentrations. Faradaic efficiency means the fraction of electrical charge that produces the intended chemical rather than unwanted side reactions. A paired flow cell configuration maintained ammonia production for more than 100 hours at an industrially relevant current density. A techno-economic model estimated production costs below $1.15 per kilogram under its stated assumptions. But this is not yet a municipal treatment plant or a global replacement for Haber-Bosch. The experiment used controlled alkaline chemistry, specialized silver-ruthenium electrodes and hydrogen oxidation at the other electrode. Real wastewater contains changing mixtures that can poison catalysts. Recovering diluted ammonia requires additional equipment and energy. Ruthenium and platinum are costly materials, and the economic estimate depends on assumptions about nitrate, hydrogen, electricity and equipment. There is also a boundary the reactor cannot erase: nitrogen pollution must still be prevented. Capturing runoff after it spreads through rivers and groundwater is harder than treating a concentrated waste stream. Still, the chemical reversal is powerful. Industrial nitrogen is manufactured, used, lost into water, and then treated as waste. An electrochemical reactor could close part of that loop, moving nitrogen from pollution back toward production. The future of fertilizer may not begin only with nitrogen pulled from the air. Some of it may begin with nitrogen recovered from water. For HQRS, thank you for looking closer.